This problem is just gets us familiar with using position vectors. I think we have the x-axis here, it's in meters, y-axis here is in meters. Then they describe some kind of flight path of an insect. So there's 2 points. One point is labeled A, the other point is labeled B, and they first ask, find the x and y components of the position vector at A. Now this is its position, and the vector indicating its position points from the origin to A. So the x and y components of this vector, there's the x component, so it would just be this x coordinate. Say it's, I don't know, say it's 3. And then this y component of this, and the notation for a position vector in 2 or more dimensions is r. Now the notation for the position vector in one direction is just x or just y in the vertical or horizontal. But when a position vector is in 2 or more dimensions, it actually has a notation r for radius. And this might be, say 6. I'm not sure where it is on yours. So that would be the x and y component. So if I was to answer it, it would be, I think the answer for this would be 3, 6. I think that's the format for part A. For part B, what's the magnitude of the position vector? Well, that would be, this is the position vector from the origin to the position of point A in this coordinate system. So for part B, the magnitude would be, you can find using Pythagoras, because this is a right triangle. There's the horizontal component, there's the vertical component. So the horizontal component is 3y, and the vertical component is 6. So a squared plus b squared is equal to c squared. You can plug in your values there and take the square root, and you'll have the magnitude of this position vector. Part C, what's the direction of the position vector at A? Well, the direction would be this angle theta. Since we know the adjacent and opposite side, in part C, for a vector here, when you know its components, its horizontal components, its vertical components, you can figure out this angle. You can use tan theta is equal to opposite over adjacent. The opposite side is the vertical component, and the adjacent side is the horizontal component. So that would be Rx, no, the opposite side is the vertical component. In this case, the adjacent side is the horizontal component. And in my case, that would be 6 over 3. And you have to know how to use the arctan, or that's equal to the inverse tan. Just different notation for the same function on your calculator. Part D, find the x and y components of the dragonfly's average velocity between A and B. All right. Well, if the dragonfly travels between A and B, I think we're given a time, aren't we? There's a delta t. Delta t is equal to 2.3 seconds, say. So there's a time. We're also given a time. Now, between A and B, there is a change in x coordinate, and there is a change in y coordinate. Now, if you fly from A to B, in my diagram, you travel downwards. Say this is 2 units downwards, and you travel over. If you take the difference between these coordinates, and let's say this is, I don't know, let's say 8 units over, then the velocity in the x direction is going to be, definition of velocity is a change in position, change in time. The change in position is the difference between these two coordinates here in the x direction. Let's say that's 8 meters. And final minus initial. And delta t, let's say it's 2.3 seconds. You can calculate that for your problem. And in the y direction, final minus initial, change in y, change in t. Very well, it may be a negative number if it's going down. It might be a positive number if it's going up. But let's say in my case it was negative 2 meters. Final minus initial coordinate in the vertical direction, and the same delta t. And I might have a negative value there for this kind of a diagram. Part E, what's the magnitude of the average velocity? Well, once we calculate these two components, I can calculate a velocity. I can calculate a velocity I can set up a velocity triangle. I know the vertical component, I know the horizontal component, so I can calculate the hypotenuse, and I would use a squared plus b squared is equal to c squared, where vx squared, this implies vy squared, is equal to the magnitude of the vector squared. And that's the average. That's the magnitude of the average velocity. You can square root. You know both of these. You can square root both sides. And what's the direction? The direction would be, let's say it would be, let's say this angle. And you can then use trig again, where, well, let's say you find, I would be interested in this angle in mine, or say this angle. And if I was, let's say I was trying to find, that's theta 1, I'll call this theta 2. If I was trying to find theta 2, I would, because I know the x, well actually I will use this diagram here. If I'm trying to find this theta 2, then I would use, I know the x and y components, I would use tan theta 2 is equal to opposite over adjacent. That's equal to Vy over Vx. So let's see, what are the lessons learned here? Position vectors are from 0, from the origin, to the point in the coordinate system. Differences in position vectors you can calculate velocities from if you know a time interval. Components of all vectors can be found vertical and horizontal using trigonometry.